Let's quickly do that first. Uh, we studied that a proton or a neutron has a magnetic field. It has a magnetic spin, a dipole. It's known as a magnetic dipole or a magnetic spin. And in a nucleus, the spins are paired, which is why nuclei they don't really have a magnetic field most of the time because all the magnetic fields are paired. So the north pole and the south pole are going to cancel each other out. Uh, ठीक है, just 1 second, Ariba. Let me. So what would happen after that is, okay, since they are paired, sometimes the odd number of nucleons, this is a hydrogen का proton है, so what happens is that the nucleus has a net magnetic field. It has a net magnetic field and it's going to point in a certain direction. There's going to be a north pole and a south pole, just like a tiny magnet, small magnet. The hydrogen nucleus or the hydrogen proton is going to behave like it. Uh, so so over here, what you do is you put the atoms in a very powerful external magnetic field, and two things happen. One of them is that the direction of the magnetic field of the protons is going to be aligned with the external magnetic field. Okay, so these tiny magnets or these atoms that are behaving as tiny magnets, they would all be aligned with the external magnetic field because the external magnetic field is very powerful. Uh, so that is known as the low energy state, and then they're going to gain radio waves, and you're going to give them radio waves. These protons are going to absorb radio waves, and they're going to gain energy, and they're going to become energetic, and they would start opposing the external magnetic field. Okay, you need energy to oppose or go in the opposite direction. So that's a high energy state, and that's known as the opposing spin. And this is resonance, that there would be an energy gap between the two states, the aligned state and the opposing spin. Uh, and that energy gap would match frequencies that are part of the radio spectrum. And it's going to be a very specific frequency. This energy gap is going to be very fixed. And there would be two factors that affect this energy gap. One of them is that the strength of the external magnetic field. That's one of the factors. That if the magnetic field is very strong, like these blue lines over here, they're very strong. Then it would be very hard for the protons to go into opposing spin. It would be very hard for them to resonate. The energy required would be a lot, and the frequency absorbed would be very high. The other thing is the other factor that we talked about was the shielding effect. That the proton is not in isolation. The proton is shielded by an electron. A hydrogen proton has exactly one electron around it, and the role of that electron is that it deflects the external magnetic field. It doesn't allow the external magnetic field to come close to the proton. It's shielding it. So in that way, if the shielding is a lot, if the electron is completely surrounding this proton, there would be a lot of shielding, and the proton would not be experiencing a very strong magnetic field because most of the magnetic fields would get deflected by the electron that's surrounding it, which is why the proton experiences a less magnetic field, and it would be easier to resonate, and a smaller frequency would be required because it won't need that much energy. Vice versa, a hydrogen could be bonded to a very highly electronegative atom like Cl. What Cl would do is that it's going to pull the electrons away from hydrogen. So the hydrogen proton, its shielding would get reduced. I mean, its electron that was surrounding it, that electron would be taken away by the Cl or pulled towards the Cl. And if that happens, the proton is exposed, and if you put it in a magnetic field, it's going to experience more magnetic field. It would be harder for this proton to go into opposing spin and resonate. So the point was that whatever H is bonded to, whatever the chemical environment of hydrogen is around it, whatever it's bonded to, it's going to affect its shielding. And if the shielding is affected, it would experience either a large amount of magnetic field or a less amount of magnetic field. And so its resonant frequency would be changed. It would be a different resonant frequency. ठीक है ये सारा, is this clear, Sarah? I mean, this is just old recap. ठीक है, अब Urera clear है? Ariba?
Yes, sir.
अच्छा, so the point was Okay, if you have a molecule and you start, you put it in an external magnetic field and the protons, you give it radio waves and they start resonating. So the ones that have the exact same type of chemical bonds that they're forming, they would resonate at the same frequency. So these three hydrogens, they would have exactly the same shielding. और मैंने कहा था कि अगर it's if there's a very slight difference even then the resonant frequency would be different. So these protons would resonate at a single frequency. These two protons would resonate. Hydrogens would resonate at a different frequency. This hydrogen is going to have a different shielding. It would resonate at a different frequency. Similarly, we did this structure. Okay, I mean it's a butane molecule. So these hydrogen protons and these hydrogen protons are exactly in the same chemical environment. They are, I mean, the type of atoms that they're bonded to are exactly the same. So which is why these two would resonate at the same frequency, which is F1, whereas these four hydrogens, they have exactly the same frequency. I mean, there's this CH2 which is bonded to CH3 and a CH2 on one side. There's this CH2 which has a CH3 and a CH2 bonded to it. So these four hydrogens would resonate at exactly the same frequency. So there would be two resonant frequencies, two frequencies that would be absorbed by the hydrogen protons to go into opposing spin. And then we did all of these other molecules. Okay, you had a propane 2-ol molecule. तो उसके अंदर these six hydrogens are in exactly the same environment. This hydrogen is in a different environment. This OH hydrogen is in a different environment. Okay. Similarly, if you had this molecule, this way all these three CH3s, they are exactly in the same environment. This H is in a different environment. So uh, F1 is going to be absorbed more, 9 times the absorption. The height of the NMR spectrum is absorption. And after that, we studied splitting. We said we did the rule, which was that the rule was that the neighboring hydrogen. Okay, we did do some explanation somewhere. So the rule was that if these three CH3s are resonating at frequency F1, let's call it F1, then the neighboring two hydrogens are going to sort of interfere with their resonance, which is why your frequencies are not going to be just unique frequencies. What would happen is that the frequencies would be split up. I mean, there's going to be interference. And the rule was, it was an n plus 1 rule, which was, where was the n plus 1 rule? I said, this is why I said this is where we did it. That the neighboring hydrogens, I mean, if these three hydrogens are going to resonate, the neighboring hydrogen protons, they're going to affect the magnetic field experienced by these three hydrogens because they have this tiny magnetic field. It might be an opposing spin, it might be a line spin. So there would be a number of ways in which these two hydrogen protons are going to affect the resonance of these three hydrogens. And the rule was the n plus 1 rule. And that was that if the neighboring carbon has n hydrogen atoms, then there would be n plus 1 peaks, which means that if this CH3 has two hydrogens, then it would be split up into three peaks. I mean, these three would be split up into three peaks. Similarly, and there was another point that we discussed, which was that the OH hydrogen proton is not going to cause interference because the lone pairs over here in NH2 and in OH, the lone pairs are going to shield both sides. So iski magnetic field is not going to interfere with this magnetic field, and this magnetic field is not going to interfere with this hydrogen proton magnetic field. So there would be no splitting if there's an O lone pair in between. I mean, the two sides would be separate; they're not going to affect each other. So I'm just to recap, I'm just going to do one more question, and let's try and keep it. Let's say I have this molecule, and the molecule is, it has an alcohol group, and over here there is a serial bond O and OH group, and let's say there's a CH3 at the bottom, and there's an H and a CH2. So the first thing is, how many absorptions would there be? How many different chemical environments are there? So this hydrogen over here is unique. I mean, it has a completely different chemical environment compared to all the others. So let's say that resonates at frequency F1. Then this OH over here, it's a completely different chemical environment that would resonate at frequency F2. These two CH2s have exactly the same chemical environment and they would resonate at frequency F3. This hydrogen has a different chemical environment compared to all the others. Uh, I mean, the types of things that it is bonded to are different from all the rest. So that would resonate at frequency F4. And these three hydrogens over here would resonate at frequency F, let's call it F5. So in total, there would be, I said in just 1 second. Okay, so in total, you're going to have 5 different frequencies that would be absorbed. So F1, F2, F3, F4, and F5. And we're going to discuss the heights and the splitting as well. So what would be the height of each peak? There's only one H in F1 and one H in F2. So F1 and F2 would be absorbed the least. So let's reduce their height because there's only one H proton. I said let's talk about F3. F3 is over here. Its height is going to be double. So this is one H proton. This would be 2. F3 would be 2. So then let's move to F4. F4 is there's only one H proton, so its height is going to be less as well. There's going to be less absorption. So that is F4, and then you have F5, which is what is F5? F5 is 3 hydrogens. I mean, this over here is F5. So it's going to be there's going to be a lot of absorption, and the relative height would be 3. So there would be, in relative comparison, if one H proton is resonating at this frequency, one H proton is resonating at this frequency, and one H is resonating at this frequency. So their heights are similar, their absorptions are similar. F3 and F5, their absorptions are greater. Okay? Yeah, the clear है Sarah? Is this clear? Sarah, is this clear? Aisha, is this clear? Abu Rana?
Yes, sir.
I
Yes, sir.
the other thing was the splitting pattern. Okay? As a first thing, I told you that OH, because of the O lone pairs, this H is completely shielded. So there would be no interference, and this H as well. So F2 and F3 are going to be singlets. So this one is a singlet peak. And this one over here is also a singlet. It's going to be a single peak, a single unique peak. F1 and it's F1, F1 and F2 basically. So this one is a singlet. What about this H proton? कितने में split होगा? Any idea? Anyone? What is the n+1 rule?
सर कौन से वाला?
ये F4 जो है, जिसको मैं पॉइंटर नहीं नजर आ रहा.
सर 7
ठीक है, 7 मतलब बहुत ज्यादा 7 तो नहीं होगा. इसके नेबरहुड में कितने? 2 हाइड्रोजन्स आर ओवर हियर, सो दैट एंड 3 हाइड्रोजन्स आर एट द बॉटम. ठीक है, रिमेंबर
6.
तो 6 और 6 का मैंने कहा था कि इट वुड बी अ मल्टीप्लेट. ठीक है, सो F4 इज गोइंग टू बी अ मल्टीप्लेट. इतनी रेजोल्यूशन नहीं होती कि वो कि you would be able to see all the peaks. So it's going to be a multiplet peak. ठीक है, so F4 is a multiplet. अच्छा, and what about F3? F3 कितने में split होगा? I mean, this H is not going to cause interference. Okay, so no splitting because of this. There is a lone pair in between. Okay, how many H atoms are in its neighborhood? Like if you look at the immediate neighboring carbon atom, it has one H. Okay, don't count these three hydrogens. You say again, okay, they're much further away. Although they're drawn like this, but these three hydrogens are much further away. I mean, immediate neighborhood. Okay, साथ वाले neighboring carbon atom, how many hydrogens? So this CH2 has on its immediate neighborhood just one hydrogen. So that means the splitting would be 2. F3 would be split into 2 peaks. And then your F5. How many hydrogens are in its neighborhood? These are not its neighborhood, which are immediately next to it. Immediate next carbon atom, there's one H. So this would be a doublet peak as well. So F5 is going to be a doublet as well. मैं इसके ऊपर ही लिख देता हूँ. This is going to be, so this one is going to be a multiplet. This one is obviously a singlet. This is a doublet. And this one is also a doublet. Okay. So this CH3 is a doublet because immediately next door there's only a carbon atom with one hydrogen. Okay. Don't look any further than that. Okay. Immediate neighborhood देखना है. महफूज clear है अबू रेरा?
Yes, sir.
Reba clear है? So, size is clear?
Yes, sir.
So remember the splitting pattern. The rule is the n+1 rule. That if the neighboring carbon atom has 3 hydrogens, there would be a quadruplet peak. If the neighboring carbon atom has 2 hydrogens, it's going to be a triplet peak, and so on. So that's pretty much it about NMR spectroscopy. Okay? What I wanted to discuss now was about chemical shift. Okay? Remember, we have been talking about frequencies. But the data booklet is going to deal in chemical shifts. It's not going to talk about, deal in frequencies. Remember, frequency and chemical shifts are pretty much the same thing. The unit for chemical shift is delta parts per million. That's the unit for chemical shift. Actually, now what is the chemical shift? The chemical shift is that when you look at the NMR spectrum, you're looking for frequencies that are getting absorbed by the hydrogen protons. Now, it's very hard to actually find the hydrogen protons and the resonant frequency. What they do is they use TMS. And the TMS peak is your reference guide. Okay? It's your reference peak. You try to look for the TMS peak. And the TMS peak is chemical shift 0. So what is the TMS? TMS is known as it's tetramethylsilane. Okay? It's tetramethylsilane. It's the solvent that is used in NMR spectroscopy. Like this molecule over here, ये molecule जो है, where is the diagram for NMR spectrum? So this molecule किसी vacuum के अंदर नहीं है. It's actually in a solution that is of TMS, of tetramethylsilane. So any molecule that you're trying to do NMR spectroscopy of, you put it in a solvent, and you can't put it in any solvent. You need TMS. You always dissolve it in TMS solvent. I said that's tetramethylsilane. What's so special about TMS? There is nothing special about TMS except for this fact that except for the fact that it has exactly one chemical environment. There's a silicon in the middle, and there are CH3 groups that are attached to it. So how many peaks would they form? In TMS, I mean, remember, this is the solvent. It's only going to have one chemical environment. It's only going to have one chemical environment. All of the CH3s, they are exactly the same. They have exactly the same chemical environment. So that's a TMS molecule, that's your solvent. And it only has one chemical environment. So there's going to be a singlet peak with a very strong absorption. So your molecule is actually floating around in TMS. And when you do NMR spectroscopy, the first thing that you're going to notice is you're going to notice a very strong peak somewhere in the spectrum at a particular frequency, and we just call it our reference frequency. As I remember, why don't you use the word frequency? The problem with frequency is कि it was factor number one. ठीक है, listen to this carefully. जब हम NMR कर रहे थे ना, what we did was I told you somewhere over here कि if you change the magnetic field, the resonant frequency is going to change. So the problem is that if you alter the magnetic field, external magnetic field, all the hydrogen protons are going to resonate at a different frequency because you're constantly changing the magnetic field. Okay, if someone is doing an NMR scan in UK and another one is doing it in Pakistan, they might not be using the same external magnetic field. And if you're not using a constant external magnetic field, the resonant frequency would always be different. Okay, so we have to think of this in relative terms. अच्छा, we have to think about this in relative terms. कि हम क्या करते हैं, हम we just ignore whatever frequency it is. ठीक है, but I don't care what frequency TMS is resonating at. I'll just say कि whatever it's resonating at, I'm going to take that as zero chemical shift. And then I'm going to search for hydrogens next to it. ठीक है, there would be hydrogens that would be resonating next to it. There might be multiplet peaks, a singlet peak, or might be a doublet peak. And then I'm going to search for these hydrogen protons. And I don't care what frequency they're resonating at. I'm going to look at the chemical shift. Okay, what's the difference between them compared to the TMS, the solvent? Like how far away are the peaks? How far are you getting the peaks compared to the solvent? Okay, so that's our criteria. And this difference, this chemical shift is not going to be, it's not going to change even if you change the external magnetic field. But आप magnetic field ज़्यादा करते हो, then the resonance would become very difficult and a higher frequency is absorbed. So all of the, I mean, this entire spectrum would shift, right? Like if you make the magnetic field really strong, then it would become very hard for every proton to resonate, and they would resonate at a higher frequency, right? Here, let me. So if you increase the external magnetic field, they would all resonate at a higher frequency, but the shape of the graph would still remain exactly the same. But they would resonate somewhere else. But the relative distance or the relative chemical shifts, they would still be exactly. So they would still remain exactly the same. The idea clear, bhai? Sara, Riba, is this clear? Abu Rara, clear?
Yes, sir.
Yes, sir.
ठीक है, तो मैं फिर से पॉइंट रिपीट कर रहा हूँ कि you use a solvent in which मतलब ये जो आपके molecules हैं, they're basically in that solvent, and the solvent has exactly one chemical environment, so you see this very strong absorption. एक तो solvent की quantity भी ज़्यादा होती है, so which is why there would be lots of hydrogen protons, and all of them are exactly in the same chemical environment, and they're going to have a single very unique peak, and it is very easy for anyone to identify that peak. And then I said that comparison is done. It's used as a reference point, and you try to figure out what frequencies, what's the shift. If there's a hydrogen proton resonating at this frequency, you look for the difference between the two. And the reason you're actually interested in the differences is कि सारों के जो frequencies है, they can be altered, they could be increased or decreased if you keep changing the external magnetic field. So which is why, just to make it constant in a way, uh, you instead start comparing them with this TMS peak. Okay, this is known as a TMS peak. So just remember, chemical shift and frequencies are pretty much the same thing. So now if I open the data booklet, in our data booklet, every or almost all chemical shifts, all type of protons and their chemical shifts are provided. ये एक सेकंड खुल जाए. अच्छा, बिल्कुल एंड पे ना, somewhere at the end, अच्छा, there, this one is probably, I mean, this is infrared, this is carbon 13 NMR, this one. ठीक है ना, focus on this. This is the chemical shift values for hydrogen protons. Remember, these values are always in a range, because even two CH3s are not exactly the same, which we just saw. हल्का जरा सा भी difference होगा ना in the chemical environment, the shielding would be different and a different frequency is going to be absorbed. So if you look over here, alkanes, I mean carbon with hydrogens, they usually typically resonate around 0.9 to 1.7 chemical shift value. Then you have alkyl, which is next to C bond O. So if you have hydrogens in a carbon chain which are right next door to C bond O, then they're going to resonate at 2.2 to 3. If you have carbon and hydrogens which are right next to an aromatic benzene ring, then they would resonate at around 2.3 to 3. फिर इसी तरह, if you have a carbon with hydrogens, right next door there's a single oxygen, then these hydrogens would resonate at 3.2 to 4, and so on. Okay, so almost all environments of hydrogen are discussed. Hydrogen next to benzene would resonate somewhere between 6 and 9. Hydrogen in an aldehyde next to C bond O, ठीक है, सारों की values दी हुई है यहाँ पे. So every value is provided. So if I just looking at the data booklet, I'm going to try and make a complete graph of a molecule. Okay, what would the graph look like? So as an example, I'm going to pick an ester. Okay, there's O, then there is C double bond O, and then there is another CH3. So how many peaks would I have? I'm going to have this CH3, then this CH3. The two CH3s are different. F1, there's F2, and then there is F3. So I'm going to get 3 absorptions, and I'm going to give them chemical shift values as well. So let's give them chemical shift values first. So what type of hydrogens are these? These are hydrogens in a carbon chain which are next to a carbon chain. So I think it's the first one. It's the alkane type. Hydrogens next to in a carbon chain. So they would resonate at 0.9 to 1.7. So I'm just going to hypothetically give them a value of 1.2. Just a hypothetical random value. And so what about these hydrogen protons? I mean, there's a carbon chain hydrogen, which is right next door, there's a single O. So find these hydrogens and their environment. It's this one. That you have a carbon in a hydrogen chain, hydrogens and carbons, which are right next door to oxygen. And they would typically resonate at 3.2 to 4. So that's what we're going to do. It's this one is going to resonate at chemical shift 3.2 to 4 chemical shift. So what about this one? It's CH3 next to a acetyl bond O. So try and look for hydrogens which are in this environment. So CH3 next to it's these ones. CH3 next to acetyl bond O, and this would typically resonate at 2.2 to 3. So this one resonates at 2.2. So now I'm going to plot them according to chemical shift values. The first one is, I said, remember chemical shift goes from right to left. So there's 1.2, then there is 2.2. I'm going to call it 2.5. And then there's 3.2 to 4, so let's call that 3.6. I'm going to get three absorptions. The 1.21 and the 2.21, they would be exactly the same. They would have exactly the same height. और फिर जो 3.6 वाला है उसकी height जो होगी that would be 2. So it's going to be 3:3:2. और फिर splitting patterns. I mean ये axis जो है ना, this is parts per million chemical shift. अच्छा फिर splitting pattern. Splitting pattern क्या होगा कि this would be a quadruplet peak क्योंकि neighborhood में दो hydrogens हैं. So make it or turn it into a quadruplet peak. So this other one would be, that was actually a triplet peak. क्योंकि it's next door there are two hydrogens. अच्छा इसकी peak जो होगी, this would be a quadruplet peak because next door there are three hydrogens. So this one would be quadruplet. And this one would be a singlet because there are no hydrogens next door. Okay, that's going to be a singlet. So remember, this axis over here is going to be representing chemical shift values, not frequencies. It's almost the same thing, except the problem with frequencies is you can change the frequencies if you change the magnetic field. And we don't want that to happen. So you use a solvent and you take the solvent peak as a reference. Or कोई भी frequency आप measure करोगे, it would be a shifted version of the. You're going to try and find what the shift is between the two. ठीक है, same चीज है. So just don't get confused with chemical shift. It's exactly the same as frequencies. ये clear है? Abu Rera clear है? Ariba, Sarah?
Yes, sir.
Yes, sir.
Achha, so just remember, okay, and try and revise this. Splitting patterns, forget the axis. Frequency, chemical shift, it's the same thing. Okay, that's not important. But boy, kid, stop thinking in frequency, start thinking in chemical shift. Think of chemical environments. How many different chemical environments would this have? This would have 4 different chemical environments. What would be the splitting pattern? What would be the absorption height? If there are 3 hydrogens, the absorption would be 3 times compared to the rest. If there's only 1 hydrogen, its relative absorption would be 1. And think about splitting pattern. Okay, if the neighborhood has 2 hydrogens, this would be a quadruplet peak. If this has hydrogens on both sides, this would be a multiplet peak. ठीक है, तो यहाँ से हम कंटिन्यू करेंगे. ठीक है, we're going to start doing questions next time. ठीक है, कोई क्वेश्चन नहीं है इस पे?
No, sir.
चले ठीक है. Okay then, take care.
Okay, sir. Okay. Allah Hafiz.